Alright, at the end of the last video we were talking about negative work done, and we were doing this example, and I didn't finish it because I knew your practice questions for yesterday weren't using negative work, so tonight's will be though, so I thought we'd come back. So in the first part of the example we were lifting an object, a 100 kilogram object, up a distance of 0.5 meters. And so we did F delta D cos theta, where the F was really mg, because when you're lifting something, it's equal to the weight acting down. The delta D is 0.5 of a meter. And the angle between the F and the delta D was 0, so cos of 0, which is 1. And you get 490.5 joules, and it works out to be positive, which means it's increasing in energy. Okay, and you don't have to write this when it works out to be positive, but I'm writing it because of what's about to happen. Because in part B I said, so what happens if you now lower the object down? And when you lower the object down, the F is still going up, but now the delta D is down. If you weren't putting a force up on something that you were lowering, then gravity would be the only force acting on it, and it would fall, right? And it wouldn't be lowered, it would just be free falling. So if we want to figure out how much work is done as you lower this object, so we do F delta D cos theta again, and F is still the 100 kilograms times 9.81 meters per second squared. It still has to balance out the weight so that it doesn't speed up going down. The delta D is still a half a meter, and this time the angle between the F and the delta D is 180, which is going to give us negative 1. So we'll get negative 490.5 joules. And remember, in physics, whenever you get a negative number, you have to tell us what it is. And what it means is that it's decreasing in energy. So in this particular scenario, because of the work being done on it, this object is decreasing in energy. Okay? So tonight you'll have questions with negative work. The other piece I wanted to talk to you about is what happens if, when you're doing work on an object, if the force is changing. So the equation F delta D cos theta holds whether or not the force is constant or changing. The problem is the force is changing, then we need calculus to solve it, because we need calculus to get the changing force. So you don't quite have calculus yet. And so the only time that we'll see problems with a changing force will be if they are graphical. So let's imagine that you have force on this side, measured in newtons, and delta D down here, measured in meters. And whoops, that line was supposed to be horizontal. If only I could draw a horizontal line. If I draw it thick enough, it'll be horizontal. So if the line is a straight line, then this is a constant force, and we can just stick it into F delta D cos theta. But if the line is going at an angle, like this, then the question would be, well, what delta D do I use? Because it's 4 up here, and it's 0 down here, and it's somewhere in between, right? And so instead what we do is we find the area underneath. So for a changing force, find the area of the graph. Find the area under the graph. This should remind you of when we were finding the distance traveled or the displacement on a velocity versus time graph. And we would find the area under the graph. So in this particular one, you would break this up into two shapes. Let's say this is 12 seconds, and I don't know, let's say this is, what's 18? It looks about half. All right, so we'd find the area of this rectangle, which would be 48, and this is newtons, and this is seconds. No, this is meters, because it's distance down here. And so when you do, so 4 newtons times, because it's a rectangle, 12 meters will give us 48 newton meters or joules. So this section is 48 joules. This is a triangle, so 1/2 the base, which would be 4 meters, times the height, which is 4 newtons, 16 take half, would be 8 joules. Did I screw that up? That's double and half and half. Assuming I did that right, 4, I'm just thinking that this should be a quarter, and a quarter of that would be 12, 16, but I get 8, so maybe it's just my diagram. Okay, and then the total you would add these together. Okay, and when you add these together, you should get 56 joules. Okay, and that would be the total. So another one of your questions this evening will be finding the areas under the graph. Okay? 8, 6. Oh, that's what I did wrong. I knew there was something wrong here. This is 6, not 4. I just knew it should have been a quarter, and it should have been working out to be 12. 24, so now this is 12 joules. And 12 plus 48 is 60. That's what happens when you make up numbers and while you're just doing the question. There we go. All right. One other little new piece for today is called power. Okay, and I know you've all heard of power. If I were to ask you what it was measured in, you might be able to get it, but we'll figure that out in a minute. But let's think about, I'm pushing a cart down the hallway. So I'm applying some force and it's traveling some distance. And you're laughing at me because it's taken me like forever to get it down the hallway. And so I'm like, but I'm not weak. I'm not. And you're like, yeah. So you say, I can do it better than that. And so I'll say to you, okay, but you still have to use the same force. And you still have to you still have to move at the same distance. But if you're actually stronger, what changes, even if it's the same force and the same distance, what changes is the time that it's done in. So like maybe it took me 10 seconds to move it down the hall, and maybe it only took you 5. We've both done the same amount of work, but you're quicker. And what that means is you're more powerful. Power is the work done in a given period of time. Okay? And so the equation is just that simple. It's capital P for power is equal to work done, W, in a given period of time over delta T. Okay? So when you go to the gym, you're doing the same routine, so the amount of work you're doing is constant, but the more and more often you do that routine, the quicker you get. So the time gets smaller, which means you are getting more powerful. Okay, units here would be joules over seconds. And we rename a joule over a second to be a watt. Power is measured in watts, and it's a capital W. Now, people always say to me, wait, but work's a capital W. It is true, work is a capital W. How do you tell them apart? If it shows up in an equation, it's work. If it shows up after a number, like 120 watts, 120 W's, that means watts, right? On your light bulbs, it's going to be a 60 watt, an 80 watt. But if it's in an equation, it's work. Okay? And so what this is telling us that we become more and more powerful if we can make our time smaller. So maybe at the beginning of the season, it takes you 2 hours to mow the lawn if you have a push lawnmower. But by the end of the summer, you got it down to like an hour and 20 minutes. You become more powerful. Or maybe it's shoveling your driveway, the same idea. There is another equation that you sometimes see for power, but not very often. Work is equal to F delta D over delta T. And delta D over delta T is just VAV. And so sometimes you'll see the equation power is equal to F VAV. Okay? But this one, power is equal to work over time, is our most constant one, okay? And the one that you will use this evening. Oh, the old unit of measure was a horsepower in the empirical system. And 1 horsepower, 1 HP, is equal to 746 watts. There's one question in your homework tonight that asks you to convert them.